So for this first part, I kind of asked you some questions in general about the unit we've been covering. Of course, endothermic things were breaking bonds like melting and evaporation and sublimation, going from solid to a gas. And then phases that are exothermic would be forming bonds. So that would be freezing, condensation, and deposition. A state function is one that depends only upon the initial and the final state. It doesn't depend on how you get there. It's path independent. The physical phase with the least amount of kinetic energy, of course, is a solid. When are we maybe forming bonds that actually would go along with your exothermic? Oh, wait. So which freezing or melting? So freezing or forming bonds. For F, I kind of told you this would be on there. Not too bad, guys. The standard conditions are for thermodynamic problems are 25 degrees Celsius and 1 bar, which is approximately 1 atmosphere. You were to go ahead and tell me what we mean by an isolated or closed system. And the way I think most comprehensively, it's that there is neither energy nor matter that is transferred from the system, either into the system or out of the system from the surroundings. So H, I've asked this question before, and all you had to do was say copper, but I kind of said why mathematically copper actually would be the higher temperature. It has the lower specific heat, zapping them with the same amount of energy, same masses, it's less stubborn to heat up. So I kind of chased it around mathematically, but copper is the answer there. So then for these, you needed to show your work. The first one is, what is the heat of vaporization? Let's see. Take that heat of vaporization that's in joules per gram and convert it to kilocalories per mole. So, of course, you need to use the molar mass. And then a really common, you're in good company if you did not remember this equality right here, that between the English and the metric system with regard to energy, 1 calorie is exactly equal to 4.184 joules. But I will say that if you went ahead and showed me your work and you didn't have the right number there, good job. So I could actually, out of each one of those was worth maybe 3 points, I could go ahead and give you partial credit. So for the next one, you were supposed to say what was the specific heat of the substance. This is kind of what you guys did for your copper lab. Given this mass and the change in temperature and the energy that was zapped, that was the Q was 24.0 joules, rearrange it and come up with the specific heat is the Q divided by mass times the change in temperature. And then on to the next one. Oh, it's going to ask me this all the time. So the last two look like this. I kind of drew a picture for C where you're talking about a system that is actually has energy coming from the environment into it, so that's a positive delta H, and actually the system is doing work on the environment, so that's a negative work term. So if you add 176 to negative 211, you get negative 35 joules. So that's the change in energy of the internal energy of the system. For D, and there was a couple of different ways to work some of these, but the answer is plus 81.6 kilojoules, and it goes something like this. This asked for what is the enthalpy of formation. That little F means formation of N2O. And this is where actually you needed to, I think, to work it. Remember that whenever we see that enthalpy of formation, what does that mean? It means the formation of 1 mole of substance from the elements in their standard state. That's how I did this. And so if you compare this, if you make it kind of like a Hess's law, and that is like our reaction of interest, if you recognize you are given the enthalpy for this reaction, which if you compare the two, if we call this 1, notice what's different about them is that this one of interest is reversed, okay? And then the other thing is it's half. So that's kind of how I did that. So then basically take this enthalpy of this reaction times negative 1/2. And I get positive 81.6 kilojoules. So again, this is where I get into the thing where sometimes some people did it differently. And it worked pretty good. You got to show your work though. And then for this one, this is kind of a factor label problem. Given this volume of isooctane, how much energy would be released? So the volume is in liters, so we have to get to milliliters, and the density was given as 0.69 grams per milliliter, so that will give us 2 grams. And then we needed to knock out the molar mass of the compound, and that will give us 2 moles. And then finally, we can go ahead and use the energy associated with the balanced equation. So it's this, this is the energy released per every 2 moles of that. So that's kind of the last term here. So then that gives you units of kilojoules. So round to 2 significant figures, because that's what you have in your volume. On to the next page. It looks like this. So kind of, I tell the story in this drawing right here a little bit. We start out basically with something that it's benzene at a temperature of 20 degrees Celsius. We're going to heat the liquid up to the boiling point temperature, which is 80 degrees Celsius, and then we're going to heat the gas up to a final temperature of 95.0. So that's kind of the story of what we have going on. So we have 3 Qs. We have the Q of heating up the liquid. We have the Q associated with vaporizing the stuff, and then we have the Q of heating up the vapor. So you can kind of see I knocked out the 2 delta T's up here at the top there. And so then the 3 Q's look like this. The Q of the first one, heating up the liquid, we use the mass of the liquid times the specific heat of the liquid. And if you're like me, it was easy to get these mixed up. So the specific heat of the liquid was that 1.74 joules per gram degree Celsius. Delta T is 60. Convert it to kilojoules just because I felt more comfortable in kilojoules, but you can do either one. And then the second one, you can see where I kind of scratched out. I thought I'd be rewriting this part of the answer key, but I'm like, no. You can see I actually started to use the molar mass of benzene, but then realized that the heat of vaporization was given in energy per gram, so I didn't need to do that. So anyway, so this is that Q2 is vaporizing the stuff. And then the Q3 is heating up the vapor to the final temperature. So add those 3 together, and I came up with 28.2 kilojoules. This one, I would say, maybe one of the reasons that y'all did better on this test than sometimes my classes do for thermochemistry is that I think that you're showing your work, and you're showing your work so I can actually understand your work, which is good for you and good for me. It helps me review it, and then I can see where if there was an issue, it's just like, oh, a transposition error or something like that. So keep up that good work. So this one was maybe the one, if I could pull you, that maybe people didn't like as much. Had a lot of people, you are in great, great company if you ask your peers. You guys knew that there was energy released during this chemical reaction because it's exothermic. And the mass, though, you thought it was absorbed into was just the mass of the reactants, the HCl and the NaOH. But the mass of what it was the energy was absorbed into was the liquid, the volume, okay, of that stuff. So you're in very good company. In fact, again, if you showed your work, I was like, oh, well, that's where that came from. So I'm like, okay. So the mass term actually we can get from volume because they said go ahead and just use the characteristics of water. So notice that our 2 volumes of the reactants, we had 33 milliliters and 42 milliliters. So you're talking 75 milliliters. Okay, using the density of water as 1 gram per 1 milliliter, of course that gives us a mass of 75.0 grams. Okay, so now you're down to 2 Qs happening within your system. You have the Q of the reaction, which is exothermic, and then have the Q of the solution that's, like I said, that 75 grams of liquid is going to take in that energy that's released. So we can track the Q of the solution by taking that mass of the solution times the specific heat of water times the change in temperature, and that last term here was to convert it to kilojoules. And so, oh, I have a little note here. I didn't go back and fix this. My SF means that on my answer key, actually, I was wrong. So to me, you were only allowed 2 significant figures because of your delta T. That's your delta T term. So this really should have been 2 significant figures, 2.1 kilojoules. So that actually propagates. Then you're ready to say that because you only have 2 things going on, then the Q of your reaction is equal to your negative Q of solution. So that means your Q of your reaction is negative 2.1 kilojoules. One last step, and if you didn't do this, and I could tell that's what you didn't do, you have to normalize it based upon, you wanted it like per mole. You could have either gone H plus or OH minus, and I want just H plus. So your moles of H plus, I calculated up above from the volume and molarity of the HCl. So the moles of H plus is 0.0396 moles of HCl. So we take the energy divided by 0.096 moles. Actually, so, but 2 sig figs, because like I said, I should have carried it at negative 2.1 kilojoules. So then the answer would be 54 kilojoules of energy per mole, or as it's written in the balanced equation. All right. On to the next one. So this one, I think it was fair game, but it was potentially challenging, I think. What I was looking for, and this was worth what, 9 points? Only 6 points. Okay, so what I was looking for was you to recognize in bold up there what it meant to calculate the standard molar enthalpy of formation of PCl3. So the standard molar enthalpy of the formation, of course, we talked, means the formation of 1 mole of substance, PCl3, from its elements in their natural state. And actually, this went on to say that phosphorus would be P4 in its solid state, chlorine would be Cl2 in its gaseous state. So then in order to work this problem, you had to recognize that this actually, it's a Hess's law problem, and our reaction of interest is, when you balance it, 1/4 P4 plus 3/2 Cl2 goes to form 1 mole of PCl3. And then with that in mind, then we could go ahead and use these equations up above that we did know the standard molar enthalpies of formation of. How can we use those to our benefit? So if you look at the first one and recognize compared to the reaction of interest, I have to divide it by 4 so that I can get my, my P, let's see, divide it by 4. Oh, divide it by 4 so I can get my P4s to line up. And then, so that means we're going to divide our heat of reaction by 4. So if you take 1774 divided by 4, you get 443. And then for the second one, to make it user-friendly, actually all we have to do, looks like, is reverse it. If we focus on the Cl2s, we have Cl2 in the reactant side. PCl5. Oh. Yeah, well, no. Oh, okay, so I know that one of y'all did this a different way. For the second one, if we recognize the PCl3, for example, I have it here as a reactant, and I really need it as a product. Okay, so if I reverse it, that falls into place. Notice then as we combine our terms, we do end up with the equation of interest. We get 1/4 P4. If we combine 1 Cl2 over on this side plus 5 halves Cl2s here, that actually is 2/2. Bring this over here, that makes that 3/2. So mathematically, this works out just peachy. And so that means that if they add up to equal that, then these add up to equal this. Ugh. Then, was there one more thing down there? Or did I just go ahead and say therefore? I think I told you before, if you see these kind of like 3 dots, that's actually just the symbol in science for therefore. Okay, so based upon all of that work, I can indeed say the enthalpy of formation of PCl3 is negative 319.7 kilojoules. So on to the next page. Is this the last page? Yes. Okay, so this was that kind of summation thing where you were supposed to look at the products, sum them up, and from the products subtract the reactants summed up. So you can kind of see how I did that. It's very easy to make a mistake on these. Okay, so that's that. Like I said, I went ahead and already